this lesson, we're going to be doing two lessons at the same time. We're going to be looking at the reciprocal function and asymptotes. The reciprocal function is very basically y equals 1 over x. In a broader sense, a reciprocal function is any function that when you multiply it times the original function, it equals 1. So we can see that if I were to multiply 1 over x times x, those two functions times each other, I'll get 1. So they are reciprocals of each other. But when we usually say the reciprocal function, we're talking about y equals 1 over x. All right. Another observation is that this function is also the simplest of all the rational functions, and we'll talk about rational functions in a little bit. So the most important thing at this point is to start exploring about the characteristics of the graphs, what transformations, what numbers do to the graphs of our reciprocal function. And so this file is uploaded to ManageBack. You're supposed to play with it, move these sliders around. So if I have a here, and if I multiply the reciprocal function by a, what happens to the graph as a gets bigger and bigger and bigger? The graph moves further away. What happens when a becomes negative? It actually flips over to the other quadrants, and as it gets smaller and smaller and smaller, it moves further away. What does b do? If I add b, it slides it up and down. What about c? What if I add c in the denominator here? It moves it left and right. As c is positive, it moves it left. As c is negative, it moves it right. So getting comfortable with all of these transformations of the graph, go ahead and play with them for a while and get comfortable with that. And when you do get comfortable with that, come back and take a look at the rest of the screencast. All right. Now, two other aspects of the graph that you need to get very comfortable with is this observation that as the graph reaches the extremes here, it actually is broken. Right? It moves up this way and then comes back over this way, and this line basically divides our graph into two areas. All right, so and if we think about it, if we substitute x equals 0 here, we get an undefined function. So as it turns out, this as our graph moves up this way, it gets infinitely close to the y-axis here, but never gets there. Same with this direction. If we go infinitely down this way, it gets infinitely close to the y-axis, but never actually gets there. Okay, so this is called a vertical asymptote. Right, and then we'll talk a little bit more of that in a bit. Now we should also notice that the graph gets infinitely close to the x-axis also. So the x-axis serves as a horizontal asymptote. So asymptotes are lines that can be horizontal or vertical, and they are lines that our graph gets infinitely close to. So that's what an asymptote is. What we're going to be able to need to be able to do is find the location of asymptotes by looking at the function and not having access to the graph itself. But we'll go ahead and practice with a few graphs. Okay, so here we go. If I'm given this reciprocal function, this is rather a rational function. So a rational function is a function where that is the ratio of two polynomials. It's the division of two polynomials. You have a polynomial in the numerator and the denominator. This is a rational function, and the rational functions have the same graphing characteristics as our reciprocal function. As we said, the reciprocal function is the most simple case of a rational function. So if I were to graph this, how can I find the asymptotes? Just by looking at the function. Well, the vertical asymptote is always found where the function is undefined. And when x is equal to 1, the denominator becomes 0, so our function is undefined. So at x equals 1, we have a vertical asymptote. And then what about a horizontal asymptote? Well, this happens when we find this by following our graph as it goes infinitely long, very, very far in this direction. We notice that the graph gets very, very close to this line in either direction. Okay, so this is our horizontal asymptote. If we follow these lines off towards infinity, they get infinitely close to this line. All right, well, how do we find that? Well, what we can do is we can substitute some large numbers in, both positive and negative, and see what numbers result. And if we keep on writing bigger numbers, we see that they both get closer and closer to 2. So our horizontal asymptote is y equals 2. Here's some notation for you. It's basically saying as x approaches infinity, positive infinity, y is approaching 2 from above the asymptote. As x approaches negative infinity, y is also approaching 2, but from below the asymptote. All right, and so that's what this plus and this minus from above, from below notation means. Okay, so from either direction, our function's approaching 2. Another way to look at this is if we get really, really large, like x is getting close to infinity, adding plus 1 to it doesn't make any impact, or subtracting 1 from basically infinity here doesn't make any impact. So we can kind of ignore the plus and minus 1 and just sort of look at the 2x over x as x is infinitely large. We can then cross out the x's and we can see that as x becomes infinitely large, we get closer and closer to 2. Okay, so let's go ahead and try this with this function. Go ahead and see if you can find where the vertical and horizontal asymptote is. Go ahead and pause. Okay, so if you go ahead and try to find where the function becomes undefined, you see that x, if x is equal to, then we have a 0 in the denominator, and then our function becomes undefined. So there must be a vertical asymptote at x equals 2. And then as x gets closer and closer and closer to infinity, this denominator basically becomes infinity. 3 divided by infinity gets closer and closer to 0. So what we're looking at is that y basically becomes, y equals -1 is our horizontal asymptote. So imagine at -1 here, a dotted line all the way across. We can see that our graphs approach that horizontal line as we as x becomes infinitely large or infinitely small. And then here's our vertical line at x is equal to 2, our vertical asymptote. Okay, let's try it again with this function. Go ahead and press pause. Okay, again, where's our function undefined? When x is equal to -2. That makes the denominator 0, and we have an undefined function. So a vertical line through x equals -2. Well, what about a horizontal asymptote? If we start putting in really large numbers close to infinity, the +1 and +2 really don't make any impact anymore, right? So we're really looking at 3x over x. The x's cancel out. So really, our horizontal asymptote should be at y equals 3. And if we look at our graph, we see that this is true. Here's our vertical asymptote at x equals -2, and right through here at y equals 3, our graph approaches from either direction, y equals 3. All right, let's try this one more time. Go ahead and press pause. Okay, so here again, same steps. We want to see where does the function become undefined when x is equal to 3. So x is 3, so 3 minus 3 makes this denominator 0. So when x is equal to 3, not -3, when x is equal to 3, then our denominator is 0, and we have an undefined function. So a vertical asymptote at x equals 3. Now what about horizontal asymptote when x gets really, really large? When x gets really, really large, this 3 and and this 9, they don't really matter. So what we really have is 2x over negative x. The x's cancel out, so we really have 2 over negative 1, which is negative 2. So I should have a horizontal asymptote at negative 2. And here we have it. So horizontal asymptote negative 2, vertical asymptote at positive 3, and then we can just put in our smooth curves, and you have just graphed this function without a graphing calculator. Congratulations.